next generation distributed healthcare platform. The main objective of our project was to integrate all our 8 distributed system experiments into one unified and practical system. Instead of demonstrating each concept separately, we wanted to build something that connects them into a real world healthcare solution where distributed algorithms actually make an impact. Healthcare is one of the most data sensitive and time critical domains. Hospitals, clinics, and labs often run on separate servers, leading to delays, inconsistency, and synchronization issues in medical records. Our idea was to solve this using distributed computing principles to create a fault tolerant, synchronized, and secure healthcare platform that can cooperate across multiple hospital nodes. That's where MediSync Pro comes in. It's a distributed system where admins, doctors, and patients interact through different portals, while behind the scenes, distributed algorithms handle synchronization, leader election, data consistency, and communication between multiple nodes. Furthermore, will be explained by Krish.
Okay, so let's talk about how backend brings together all our distributed systems experiments. MediSync Pro runs on multiple connected nodes, and each one performs a specific role in maintaining the distributed healthcare network. We have implemented 8 key distributed system concepts, and here's how each one fits in. Berkeley clock synchronization algorithm. Used in admin command center, this feature ensures that all healthcare nodes, hospitals, labs, or clinics have perfectly synchronized clocks. Every few seconds, the admin node acts as the master, collects the current time from all connected nodes, calculates the average, and then sends the correction values back. This prevents issues like mismatched timestamps in patient records or medical test reports. Second, mutual exclusion algorithm. This algorithm implemented in the doctor portal under medical record update system. When multiple doctors update the same patient record at the same time, the mutual exclusion algorithm ensures that only one doctor gets access at once. It locks the shared resource until the update is complete, avoiding data overwrites and maintaining data integrity. Third, election algorithm. This experiment is used in a dynamic leadership management module. When the main coordinator fails or disconnects, the system automatically runs the bully algorithm to elect a new coordinator among the remaining nodes. This ensures continuous operation with no single point of failure, crucial in a healthcare network where downtime can affect patients' care. 4. Data replication and consistency. This experiment powers a patient data module. Each node holds a copy of critical patient information. When one node updates its data, it instantly replicates it all across other to maintain consistency. If a node goes offline temporarily, it syncs automatically once and it reconnects. 5. Client server module. This forms the foundation for entire system. The doctor, patient, and admin portals communicate with the backend servers through REST APIs and real-time socket IO events. This ensures instant message delivery. For example, when the doctor adds a diagnosis, the patient immediately gets a notification on their dashboard. Next, I would like to call upon Rohan for front end.
Now, let's explore how these backend experiments connect to our frontend. Our frontend is built with vanilla JavaScript, HTML, and custom CSS3, featuring a dark theme with glass morphism design for a sleek, futuristic health interface. We designed three main portals: Command Center, the admin panel. This panel integrates Berkeley clock synchronization, election algorithm, and distributed logging experiments. Admins can monitor active nodes, check network health, and even visualize node performance analytics. Whenever the coordinator changes, it updates live on the dashboard thanks to real-time WebSocket events. Next is the doctor portal. This section demonstrates our mutual exclusion and client-server communication experiments in action. Doctor can log in securely, access their patient list, edit or add medical reports, and see instant updates from other doctors. Every update triggers synchronization across all connected nodes, maintaining live collaboration between hospitals. Next, patient dashboard. This dashboard demonstrates data replication, consistency, and security experiments. Patients can view their complete healthcare profile, see real time updates, and track health metrics. Even if one node goes down, their data remains accessible from another, providing the effectiveness of our replication mechanism. On top of that, we have used socket communication experiment to enable instant notification such as when doctor uploads new prescriptions or test results. Next, I would like to call upon Anirudh.
So now let's discuss deployment and security, two areas where we have combined the remaining experiments. So we implemented a role-based access control, our security experiment, to ensure only authorized users access the specific data. Admins manage the network, doctors handle the patients, and the patients can view only their own records. All communication between the nodes is encrypted, and every activity is logged for auditing and the compliances. Our RPC experiment is applied internally to enable the node-to-node communication. Instead of traditional REST calls, certain tasks like coordinator messages or application updates use RPC style messaging, improving the speed and reliability in the distributed coordination. So, we have a logger module inside the admin panel that continuously records the events, node startups, synchronization times, error logs, and the user activities. This comes from our distributed log experiment, providing real time monitoring and analytics through graphical metrics. For deployment, MediSync Pro supports the both local and the cloud setups. We can launch multiple nodes using the node server.js or scale across servers using the Docker Compose for real distributed simulation like Docker Compose up-d easy it is a command. This modular setup let us simulate a complete hospital network where every node represents a hospital or lab communicating, synchronizing and staying consistent. So for conclusion, I will like to invite Aryan.
In conclusion, MediSync Pro successfully combines our 8 distributed system experiment into one powerful real-world project. First, Berkeley clock synchronization. Second, mutual exclusion. Third, election algorithm. Fourth, data replication and consistency. Fifth, client-server communication. Sixth, remote procedure calls. 7. Security and authentication. 8. Distributed logging monitoring. By integrating these experiments, we created a system that is fault tolerant, consistent, synchronized, and secure. Everything a modern healthcare infrastructure requires. Looking ahead, this platform can be expanded into a real hospital management system with features like AI based diagnosis, telemedicine integration, and blockchain based patient records. With MediSync Pro, we have not only demonstrated distributed system algorithms, but we have built a model that shows how technology can truly empower healthcare.
We brought the theory of distributed applications into real application.
Designed a seamless, secure, and visually dynamic user experience.
And ensure that every component communicates efficiently and reliably.
Together, we present MediSync Pro, empowering healthcare through distributed technology. Thank you for watching.
Thank you.